Hello, this is video 3 in a little mini series on probability measure. The first video was on set theory, the second one was on fields and the properties of fields, and now we're going to extend fields to something called sigma fields. And there's a lot of repeat here, and so what we proved in the second video of fields, we'll just say, it's very similar to this, we're going to move on, just so we can cover more topics. So the definition is this will look very similar to a field. Now, mathematicians tend to call this an algebra or a sigma algebra. Statisticians tend to call it a sigma field. Not sure why the different notation, but I'm going to call it a sigma field. And as we go through these, the only difference is this last one here, this last condition. So here we have a class of subsets denoted by U. Now these three properties have to hold for it to be a sigma field. U is non-empty. If a set is in U, then its complement has to be in U. Now this third criteria for a field was that if A1 and A2 were in the field, then their union or their intersection also has to be in the field. But it's a finite union or finite intersection, where a sigma field extends it to a countably infinite. Okay, so we have A1, A2 up to, keeps going. It implies that this union is also back in U. And we're going to look at, I have one example where the set, or the class is a field, but it's not a sigma field. But if it's a sigma field, it's also a field. So some corollaries from this. The entire sample space and the null set has to be in U. Now the definition or the requirement says that this countable union is in it, so that there's infinite. But using just these three, we can also deduce that the intersection, countably infinite intersection, is back in U. And the proofs of these are very dissimilar to what we did in fields, so I'm going to pass those. Now, I mentioned earlier that a sigma field is a field, but a field is not always a sigma field. And here's a quick example. So, in C4, the class that we introduced in the previous section, if our sample space is infinite, and then we want all the sets such that A or A complement is finite, okay, and this was a field, okay, and we proved that. So let's see if it's a sigma field. So let's let S be the real number line, and we're going to let this set be all integers in this closed interval, okay, for J equal 1 to infinity. So this is a field, okay, and we proved that it has to be. But is it a sigma field, okay? And the answer is no, because it's not a field, because if we take this infinite union of these intervals, where if we did a countable union, this is going to be finite, and its complement would be infinite, but they would be in the set because that's how we define what this set was going to be. But if we take an infinite number of these intervals, then this is infinite, and its complement is infinite. And so they're both infinite, so it's not in the set. So it doesn't fulfill the requirement of a sigma field. So anyway, but that's kind of a simple little example to show you that a sigma or a field is not always a sigma field. So let's look at some examples here. Here's the trivial set where it's just two elements. It's called trivial sigma field. And then we have what's called all subsets, or the discrete sigma field. Some would call that the power set. Then here's a set, a class of sets where it's 4 elements. This also is a sigma field. And class 4 is if S is uncountable, so infinite, we want all the sets A such that A or A complement is countable. And this is a sigma field. And we're going to prove that because it starts, helping us in later videos. So how do we show that this class is a sigma field? Well, it has to meet the 3 requirements. Okay. So if we the complement of S is the null set, or the empty set, and it's countable, so that means C4 is non-empty because those 2 are in it. If A is in C4, now we need, the property 2 says that a complement has to be in C4. So, but if A is in C4, then A or A complement is uncountable. So now we have to go through both scenarios to show that in both, if this is countable or this is countable, then that still shows us that A complement is in C4. So let's if A is countable, then A complement is A, but that's countable. So that implies that A and A complement, specifically A complement's in C4. And 2, if C complement is countable, well then it's automatically in C4. So if we have a set in C4, its complement's also in C4. Now here, property 3, that the countable union is back in C4. So let's let AJ be the sets from 1, 2 to infinity. Let them all be in C4. Then we have 2 conditions. Either they're all uncountable, either they're all countable, or at least one of them, at least one of the AJs is uncountable. So we're going to go through those 2 cases. So we're going to let every AJ be countable. Okay, that means this union is countable. Okay, which means it's in C4 because this is a countable set. Okay, well, 2, there exists an AJ that's uncountable. Okay, remember, only the AJ or A complement has to be countable. So let's assume that one of them is uncountable, meaning its complement is countable, which is this. So now, see, we need to show that this union is the complement of, this union is in C4. So if we look at this union complement, then that is equal to this intersection by De Morgan's law. Well, since one of these AJs is countable, that means this intersection is countable, right? So this set's complement is countable, so that means that this set and its complement are both in C4. So this also has to be in C4. And then we've just shown that we've satisfied the 3 criteria of a sigma field. So let's look at a couple theorems here. We have 2 pages left. Now this is very similar to what we did in fields, but we're going to do with sigma fields. We're going to let I be an index set where I can be finite or countable or uncountably infinite. And we're going to let UI be all the sigma fields in of our space. So it's that's just kind of worded weird, because whenever you talk about a sigma field or a field, you need a sample space or a universal set. So these are going to be all the sigma fields in, from our sample space. So let's let U be the intersection of all those sigma fields So this intersection means that we want all the sets A such that A is in every single one of these sigma fields for the whole index set. Well, this intersection is then a sigma field. Now, we proved it for the fields, and this proof is going to be so similar that we're going to move on to save a little time. Now, Theorem 4, so I'm going to refer you back to the video 2 on fields. Now here, we're going to let C be an arbitrary class of subsets of the sample space or the universal space. We're going to let U be a unique, so this could be one element or two or three or a set or the whole thing. We don't know. It's just a subset of our sample space. We're going to let U be the unique minimal sigma field containing C. So that means that of all the sigma fields that contain C, then we want the smallest one of those. And we're going to let U denote that. And U is called generated by C. So it depends upon what we have for C. So if C starts out small, then this sigma field will be a little bit smaller. But if it's the whole set, well, then the sigma field is the power set. So anyway, but it is a sigma field. We have a unique representation of that. We know how to generate these sigma fields from a unique arbitrary set. And actually, in the next video, when we talk about probability measure, we're going to generate a few of these, and specifically the Borel sets. But more on that later. And we proved this for fields, and the proof of this is very similar, so I'm going to skip it. And refer you back to the second video. So now once we have the mechanisms of a sigma field, now we can start talking about measurable spaces. So whenever we have a universal set and an associated sigma field, this space is called a measurable space. Okay. And so S is non-empty. It has to be non-empty, and U is a sigma field. Note there's no measure or probability measure associated with this. But if we can set up these two requirements, now we can put a measure on it. It's called a measurable space. And here's sort of a couple silly examples, but I think it'll drive the point home. So here's our sample space of 1, 2, 3. And now we have a sigma field. It's the trivial sigma field of the empty set in S. Okay. So then this tuple, the sample space and this sigma field, is a measurable space. We can put a measure on that. So here's another example of using the same S, so our same universal set, and then we let the sigma field be the power set of S. Now then this tuple, S and U2, is another measurable space. So we can have multiple measurable spaces from a given universal set, okay? But we have to have the requirement of a universal set and a sigma field upon that universal space. So then, let's, this remark is for later. So after next video, we're going to look at probability spaces. Then I think we're going to go into what's called conditional probability. I haven't decided that yet. But this will play a part in that. So let's let U be a sigma field, okay? And again, this needs to be associated with a universal set. So I probably should always put that, but I didn't this video. And let's let this set be an element of the sigma field, okay? We're going to create a new class, okay, called UA. And it depends upon the randomly picked or not randomly picked set A. We're going to intersect every element of our original sigma field with A. Okay, so it's the intersection of every single element in our sigma field with A. Those are the sets that we get. So I'm saying this class UA is also a sigma field. Okay, so this is important in conditional probability, where you say, what's the probability A given B, right? So this acts, or I probably say, what's probably a B given A, since this is the set. This acts as our new sample space, and we have a new sigma field from S. So anyway, so let's go through this proof. This is the last one. U is in, or the empty set is in U, because U is in the original sigma field, and this intersection is the empty set, so it's in UA, so it's non-empty. Now the second condition, if we have a set in UA, then its complement has to be in UA. So then if C is in original sigma field, then there's a B in the original field. There exists, that's what that means, a B in U, such that this condition is held. Okay, so now we know that B complement is in this sigma field because it's a sigma field, and so if we let C2 be this complement, that intersection we call C complement, it also has to be in U field. So C and C complement are in our sigma field. So now we have an infinite number of sets in our sigma field, or UA. Then we have to show that the union of those is back in A. So if C, we're going to let C be this infinite union. But C's are derived from this, where this is an infinite set, or infinite sequence of sets in our original sigma field. So this is equal to that. Well, since intersection is distributive over union, we can rewrite this as A intersect these unions. Well, this is a set in our original sigma field. So that means this set, which is C, has to be in sigma A. And so since this is in our original sigma field, and we intersected it with A, then that implies it has to be in UA, our new sigma field. Okay, so this plays a part in conditional probability. So the set A plays the new role of the entire space, because the sample space intersect A is A. So this really plays as our new sample space. And this is going to be a part of conditional probability in a couple videos. Well, that's all I have today. Next video is on probability measures. So we're going to take this measurable space and put a probability measure on it. So anyway, hope you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. Thanks, bye.